Hello, my name is Max Alekseyev. I'm from George Washington University, and it's my great pleasure to present results of recent study of generalizing Ramanujan extension of Faulhaber formula in which we used formal Bernoulli series. So let us first discuss what is Faulhaber formula and what is the Ramanujan extension of it. Faulhaber formula expresses sum of first n positive integers, each raised to the same power p, whereas p is a positive integer as well, and it expresses this sum as a polynomial in n, in which coefficients depend on the binomial coefficients and Bernoulli numbers. So expression given here on this slide. And then the natural question is, there exists a similar formula for fractional powers p. The study of this question was pioneered by Ramanujan in his 1915 paper titled On the Sum of the Square Root of the First n Natural Numbers, in which he introduced function tau of n and m. M should be at least 3. Both n and m are non-negative integers. Tau function defined as the infinite sum, in which we sum over nu from 0 to infinity, and the term is square root of n plus nu plus 1 minus square root of n plus nu, and this difference raised to the power m. So this series converges for n greater than or equal to 3, so everything is fine here. And what Ramanujan did, he considered the sum of first n positive integers raised to the power p. There p is now half integer, namely 1 over 2, 3 over 2, 5 over 2, or 7 over 2. And he expressed such sums in terms of this tau function and a polynomial in n. So more specifically, Ramanujan proved existence of constants C1 and C3 such that the sum of square roots of first n positive integers equals this constant C1 plus 2 over 4 over 3 n raised to the power 3 over 2 plus 1/2 of square root of n plus 1/6 of tau of n 3. So m is equal to 3 in this expression. And there is a similar expression for sum of positive integers raised to the power 3 over 2. And he further noted, and this is the direct quote from his paper, that the corresponding results for higher powers are not so neat as the previous ones. Still, he gave two more expressions without the proof, so we can see that expressions have similar shape but become more complicated as the power grows. And this formula remained isolated for over a century, calling for generalization, and we are going to give such a generalization to arbitrary positive half integer power. So let's first reproduce Ramanujan's proof for the power 1/2. That is, we want to sum up square root of first n positive integers, and we consider function. So we want to prove this formula shown at the top, and we consider function phi sub 1 of n, which would be the difference between the sum of interest, the sum of square roots, minus this expression that we want to prove. So C1 will be defined such that phi of 1 is equal to 0, so it's easy to verify that indeed C1 is this constant. And then we consider the difference between consecutive values of phi1, and it turns out that this difference is identically 0, so it doesn't depend on what is n. The difference between consecutive values is 0, and applying summation of these differences, we obtain that phi sub 1 should be identical 0. Now let us generalize Ramanujan expression, and I start right away with such a generalization. So I give a generic formula which works for arbitrary half integer power k over 2. K here is an odd positive integer, and you can see that this sum is expressed as constant c sub k plus square root of n times certain polynomial of n, polynomial of course depends on the value of k, plus the sum of values of function tau of n I, so n remains the same here, but value of m, second argument of tau, changes, and it goes over odd integers starting at 3 and ending at integer k plus 2. And there are certain coefficients denoted a with lower index I and upper index k. So the expression for these coefficients given down below, and it involves binomial coefficients as well as Bernoulli numbers again. Also, we see expression for the polynomial p sub k of n, which also depends on binomial coefficients and Bernoulli numbers. And finally, the constant c sub k defined very much like the constant c1 was defined. So we will see how all these play together later on. Now, if we compute coefficients a, I, k for different values of k and I, we will see the following pattern of values. You can see in particular that if I is equal to 1, then the corresponding coefficient is 0, and other coefficients, we see zeros appearing like in chessboard mode. And we are actually going to prove that this is not a coincidence, and indeed we have those coefficients equal to 0. Now let k be an odd positive integer, so let me present proof outline. So the first thing that we'll do, we will express our coefficients and the polynomial p sub k in terms of Bernoulli series. Then we establish a duality property for Bernoulli series, which will be used quite a lot. And in the proof, then we establish cases, then coefficients a equal to 0, derive a formula for convolution of those coefficients with an arbitrary series. Then we express function tau in terms of Chebyshev polynomials, and then using generating function for Chebyshev polynomials, we will combine them with the previous results to generalize Ramanujan's proofs to an arbitrary half integer power k over 2. So let us first establish connection to formal Bernoulli series. So we define formal Bernoulli series with index alpha. Alpha now is any real number, and it's going to be an infinite sum in which I goes from 0 to infinity. The terms in this sum are binomial coefficients alpha choose I times Bernoulli number b sub I times indeterminate z raised to the power I. So this series should be considered as formal series, as it converges only if alpha is not an integer, it converges only for z equals 0. That's why we are going to treat it as a formal series. But if alpha is equal to a non-negative integer, let's say m, then the series in fact represents a polynomial which is called reciprocal Bernoulli polynomials, and it is essentially what it is. It is a reciprocal polynomial of the Bernoulli, of the conventional Bernoulli polynomial. Then using the property that Bernoulli numbers are 0 with odd indices, except for b sub 1, which is minus 1/2, we can easily just establish the following relation between value of our Bernoulli series with at minus z with that of z. In fact, with b sub alpha of minus z is equal to b sub alpha of z plus alpha times z. So very simple relationship. But in fact, between those two values, there exists a bit more complicated relationship, which I call the duality property, and which is stated in this theorem 1. So you can see here that we have any power series denoted h of z. Again, alpha is a real number and m is an integer. And it turns out if we multiply our Bernoulli series by this h of z, series h of z, and express extract the coefficient of zm, that it is the same as extracting coefficient of z to the power m in the following expression: h of z over 1 plus z times 1 plus z raised to the power m minus 1 minus alpha times b sub alpha of minus z. So it is indeed, this formula again connects a value of Bernoulli series of z and that of minus z, but now it involves an arbitrary power series h of z. So I'm not going to present the full proof, but I'm going to present some ideas behind it, the key ideas behind it. So the first observation is that the identity in this statement is formed by polynomials in alpha, and furthermore, the degree of polynomials is at most m. And therefore, it's sufficient to show that this identity holds for any positive integer alpha. Then for a positive integer alpha, the statement turns into one about Bernoulli polynomials. And Bernoulli polynomials have very nice properties that we can use. And the final ingredient in the proof is using Lagrange inversion theorem. So from now on, I will assume that this theorem is established. And then with its help, we can come up with a sort of generating function for coefficients a, ik, and polynomial pk of n, and establish as well that the pattern of zeros among the coefficients a. So you can see particular expressions here, and those expressions involve yet another power series denoted C of z, and which is in fact the generating function for Catalan numbers. So the explicit expression given down below. Then we can come up with the following statement, which essentially represent a convolution of our coefficients a with coefficients of any power series denoted f of z. So if we take this sum here goes over at positive integers starting at 1, ending at k plus 2, and we extract the coefficient of z I minus 1 over 2 from f of z multiplied by coefficient a ik and sum up over these values of I. We in fact can give two closed form expressions. So in fact we need them both. So you can see those expressions shown on this slide here. So let's take it as a proof. And now we are ready to give a generalization of Ramanujan proof to our formulas. So, but in order to do so, we need first represent function tau in terms of Chebyshev polynomials of first and second kind. So we start with expressing this difference raised to the power m, difference of square roots of n and n plus 1 raised to the power m. It is in fact square root of n times u m minus 1 of square root of n plus 1, u is the Chebyshev polynomials of first kind, minus square root of n plus 1 times t sub n sub m of square root of n plus 1 divided by square root of n plus 1, and t here is the Chebyshev polynomials of second kind. So in fact, those two things are u of u sub m minus 1 of square root of n plus 1 and t sub n of square root of n plus 1 divided by square root of n plus 1 represent polynomials in n. So it is, this expression is square root of n times polynomial of in n minus square root of n plus 1 times polynomial in n. Furthermore, we can come up with generating functions for those values of square root of n plus 1, and this generating function is easy to obtain as bisections of generating functions for conventional Bernoulli, sorry, not Bernoulli, but Chebyshev polynomials. Now, using the convolution property for coefficients a and the generating function from the previous lemma, we can obtain the following expression in which we compute the convolution of our coefficients a, ik with the values of Chebyshev polynomials. So it turns out that we both are expressed in terms of our polynomials p sub k. In one case, it will be just p sub k of n. In the other case, it will be p sub k of n plus 1 times square root of n plus 1 minus n plus 1 raised to the power k over 2. Now we are ready to generalize the proof of Ramanujan, which was given for function phi of phi sub 1 of n. For an odd positive integer k, we define similarly function phi sub k of n, and it's going to be the same way sum of powers k plus k over 2 of first n positive integers minus the expression we are going to prove it is equal to. The constant c sub k defined in a way that value of phi sub k of 1 is 0. Then we use expression for the difference of these consecutive square roots in terms of Chebyshev polynomials, as well as values of a with a lower index 1 being 0. And the previous lemma, we established that the difference between consecutive values of phi sub k is 0. And from here, our main theorem follows instantly. So we prove that the sum of powers k over 2 of first n positive integers is indeed what we claim it to be. And this concludes my talk, and I would like to just go with acknowledgements. First of all, I'd like to thank you, my co-author, Cesar Valverde, as well as students in his lab who co-authored this study. Also, I'd like to thank Mass Overflow, which linked our expertise. Essentially, the project started as a question in Mass Overflow, and this question actually jump-started our collaboration. So if you're interested in more details, please read our paper, which is titled Generalization of Ramanujan's Formula for Sums of Half-Integer Powers of Consecutive Integers via Formal Bernoulli series. And it is published in the Ramanujan journal, as well as preprint. You can see information on this slide. And thank you for your attention.